Okay, and like for the other materials, we will follow more or less common type of agenda. We will see, we will see how glass is made, some terminology, some types of packages, how packages are produced, and some considerations on bottles design, physical and mechanical properties, and the closure systems that are used in this type of system. Okay. So we deal with glass. We have glass in our windows. We have glass in our cars. Okay, and we have glass in our packaging, and we have different compositions for different applications. And generally, glass is defined as an amorphous, inorganic product resulting from the melting that was cooled without crystallization. So we have not a crystal, but an amorphous material. And so, as I was saying, we have different compositions, and for packaging, we use what we call soda lime glass, because the major components are, besides silica, are sodium and calcium. This is different for other applications, like glass for ovenware or glass that we have in the laboratory. So we have other types of compositions. And so glass is said to be a highly viscous liquid, supercooled liquid. I don't know if you had the chance. I had in my grandmother's home windows, very, very old house. I still remember to see the first windows with the glass a little bit thicker on the lower part as compared to the upper part. Do you know what I'm speaking about? Some yes, some no. So it means that if the time scale is very, very, very long, we can see glass as a liquid. It means it drops. Yeah. So, but this was in my grandmother's house, and now the glasses are different, new ones, and we cannot see this any longer. Anyway, this is important for the properties of the glass. So its molecular units have disordered arrangements. There are sufficient cohesion, so we have mechanical strength, but still we have a highly viscous liquid. And the basic structural unit is silicon and hydrogen combined in a tetrahedron type of structure. Like we see here, we have the silicium or silica, and then we have the oxygen atoms connected. And the silica, that's the major ingredient. It comes from sand. It provides the structure. It requires a very, very high level of energy to melt, because it melts at 1,700 Cs. So glass is highly energy intensive, demanding type of packaging. So this is the major ingredient. Then we have two other groups, that's the sodium and potassium carbonates and the calcium and manganese carbonates. This group, sodium and calcium, particularly sodium, decreases, they both decrease the fusion or melting temperature and decrease the viscosity of the silica. So they are important in the recipe to decrease the temperature of melting and therefore to decrease the energy requirements. And the calcium and magnesium carbonate, they come from minerals like the limestone and dolomite, and they work as stabilizers. So they increase the resistance to water, okay? Because without these, the glass would not resist very well to water. Then we have further ingredients like aluminum oxide that increases hardness and the durability of the glass. And most importantly now what we cool it. That's the recovered glass in order to be recycled. So the glass industry calls it cullet. That's the glass that is recovered from post-consumer recovery systems, and they are very important for this industry because not only they allow for saving raw materials, which is very important, but also they allow for saving energy. Why? Because the energy to melt something that is already a glass with this structure is lower than the energy required to melt sand. So if we are melting already glass, the energy required is lower. That's why several decades ago, glass industry started to collect bottles, use post-consumer bottles in everywhere, not exactly because they were concerned about environmental, but because they saved money, because they saved energy. Besides these other materials, other ingredients are used like production heads, like colorants to do glass in different colors and so on. Okay, so this is the final typical glass container, so bottles composition. So we have more than 70% is the silica. Then we have the sodium phase, the calcium phase, and the rest is a much smaller percentage. Okay? Any question right now? So this is a formula with numbers. So to produce around 1,000 kilos, we may use as much as almost an half of it of cullet, which means recovered glass, and the rest with raw materials. Industry, glass industry can use as much as cullet as possible, because from the safety point of view, there are no problems, because with temperatures higher as 1,700 or 1,400, such a high temperature, there is no contamination, no problem in terms of industry can obtain exactly the same performance of a glass bottle, which is not the case for the other systems like paper or like plastics. So this is highly able to be recycled in higher rates. Okay, about the terminology of a bottle. We have the finish. We call it finish, or industry call it finish, the upper part where the closure is applied. And this is a very important part, like all, but these dimensions must be compatible to the closure that is going to be applied, and this is standardized. We are not able to select or to decide that we want, okay, we have wider and shorter, but we have standards, and we don't have a continuous range of dimensions to select. And then we have the neck that is cylindrical, and the cork is applied on the finish and the neck. So I use this example as a wine bottle, of course. So neck is very important also, because the cork will continue into the neck portion, and we will see how and why neck is important. Then we have the shoulder, that we may have different slopes here, and the resistance of the bottle, it will depend a lot on this shape of the shoulder. And we have the body that supports the label panel. And here we have the punct. The punct is this inside portion of the glass of the wine bottle. Then we have the heel, and in most bottles we have orientation feature that is required for positioning the bottle according to the label place. Okay, if we have circular bottles, and if we have, as we do normally, automatic labeling machines, we want to turn the bottle into a position where the label will be applied. So this thing on the bottles is required to the machine be able to orient the bottle and place the label on the right position. And on the bottom, on the base, we have some traceability marks. That is very hard to show, but here maybe we can see we have a B and A, that is the name of the producer of the bottle. Then we have some codes that indicate the type of the bottle and the period of time the bottle was produced. And why is this important? Because if there is a breakage, if the bottle breaks in the filling line or in the consumers, we want to trace back and understand why the bottle broke. Because a problem of the production, because a problem with the handling, whatever. So it's important to identify precisely the mold where the bottle was produced, so the trace marks are important. And here we have again the push-up or the punct that increases the resistance to internal pressure of the bottle, and it's important in carbonated drinks, so in champagne, in beer, high carbonated, with high internal pressure bottles is important to have this shape inside. Regarding the type of packages, we usually designate a bottle or a jar according to the format. According to the color, we have this range and others. These are a few examples. We call these amber, black, blue, green, and flint. Flint is the like the ones you have there without no color. And according to the use, we can say that they are reusable or refillable, or we can say that they are one way when they are returned back to the recovery system after the first use. Okay. Any question? So this is quite straightforward. Regarding the production steps, so we have the mixing of the ingredients and the melting. Then we have the forming process, and we have basically two types of forming processes, one that is called blow and blow, and another one that is called pressure and blow. It's more or less like we saw yesterday for the plastic bottles. Remember that we have seen we had two steps. In that case was the extrusion blow and the injection blow. In this case, we also have a blow, because there is no way to do bottles without blowing. But then the first step is, it can be a pressure or a blow. We will see. Then we will have the annealing step. Annealing step is a step where we increase the temperature a little bit and decrease again in a controlled way to free out tensions, surface tensions that the glass has, and that will make the bottle very, very fragile. So annealing is an important step to increase the mechanical resistance of the bottle. We have surface treatments where we applied some coatings on the bottle. We have basically two, the hot hand and the cold hand, that I will explain this a little bit later. And then we may have other operations like printing, sleeving, and of course inspection and final control. So this is the first overview of the production steps of glass bottles. This is how the line is organized. So we have big silos where the raw materials are. Then we start here to compose the ingredients from different from different types. So we prepare the recipe, let's say here. Then we go to number 2, where we have the oven, where we melt the ingredients. Then in number 3 and 4 we have the molding, so where we actually shape the bottles. Then we have the surface treatment. The first surface treatment here is number 5, is applied in here. Then we have the annealing step. This is wrong. The number 6 is annealing. So then we have number 7. We have the cold treatment here, and here, yes, we have the inspection, and finally the packaging, the producing of pallets of bottles, the preparation to send the bottles away. So I need to take note of small mistakes to correct them. So this is an image that we can see from the oven. So it's a little window from where we can look into the inside of the oven. So there is a mixing and melting, as I indicated already, at very high temperature. And the temperature is typically, after those ingredients used, is about 1100. And there is a scissors that cuts the glass in a piece of glass that goes to be a bottle. So a fragment of glass with the weight required to produce the bottle, and it's called the gob. Then we have the blow and blow process first. And in the blow and blow process, so the gob enters on the first mold. Then there is a baffle that is closes the mold, and then there is the blowing air, and we form a little bottle that we can see here in yellow, that then goes to the second mold. And in the second mold you see here the little bottle, okay? And we have more blowing air again, and we have the final shape of the bottle here. So is in the first step and in the second step we have air blown to shape the bottle. In the case of the press and blow process, in the blank mold, we call a blank mold, we don't use air, but we use a metal element to shape the blank or the pre-mold or the first bottle. Then the preform goes into the second mold, and then we have a blowing step, and we have the finished bottle again. It's clear? Good. So my question now is, what do you think gives the best bottles? The blow and blow or the press and blow? The press and blow. Yeah, the press and blow, it tends to give bottles where the thickness distribution is more uniform, and therefore we can decrease the overall weight, because we can decrease the thickness, because we are more sure that we have the minimum thickness in all places of the bottle. This is a more advanced method or process to produce. Okay? So in here we can see the bottles just arriving to the second step and the bottles leaving the second step. You see that they are very shiny, very hot, because everything is very quick, very automatic. It's very fast. So this transfer, there is a transparency between the first mold and the second mold, and this is one example how the bottles leave the first mold, and this is this is how they leave the second mold. Okay? So this is why we have here the press and blow applied to produce lightweight bottles, typically. Yeah? Any question? Okay. Now, annealing. Annealing, as I said before, refers to the step where the stress resulting from non-uniform cooling during forming and handling the bottle after molding, these stresses are removed. I should go back again to that picture. You know, this picture shows that the bottle is very hot and touching metal parts that are cooler. So let's say that the bottle is forced to cool down in an uncontrolled way, and because of this, the bottles remain with some stresses. So annealing is when the bottles are reheated, but in only to 400 or 500 degrees C, no up to 1000, because then they will melt again. No, just that they are warm up just to 500 degrees C, so they are not soft to change dimensions, but they are warm enough to liberate, to get out of these tensions. So there is a long oven that we saw in that scheme, and they are all at this high temperature for a few minutes, and then they are cooling down slowly. Regarding the treatments, the surface treatments, these are like makeup on our skin. So they increase strength by lubricating or protecting the surface of the glass. So the hot hand treatment is applied before annealing, and it prevents surface damage. It provides strength, and the cold hand treatment is carried out later, so after the annealing, and increases lubricity. it provides low friction coefficients. So in the filling line, the bottles are able to run at faster rates and without scuffing or scratching each other. Okay, so this is very important for the resistance of the bottle, is to avoid scratching on the surface. So this is like a makeup to reduce the coefficient of friction. So this is performed by spraying an organic coating, a polyethylene, wax, or typically. So it's really like a makeup. It's a wax or silicones also applied on the surface. This is another type of surface treatment that it is a sleeve. So it's like a all-round label. So this is applied on the glass manufacture. Is not on the filling company. So sleeves are made out of plastic that shrinks. They can also be in PET. It's also common. So they have a special machine. They applied the sleeve on top of the bottle. They apply heat, and the sleeve shrinks around the glass. So it adheres to the plastic, is all around. It's already printed, so the bottle is already decorated and labeled and so on. So it provides a high level of protection. Why? Because as it is all around, if in the event of the bottle to break, it keeps the fragments. So even if the bottle breaks, is bad because we waste the product, but in terms of safety, is very important because the fragments are contained, are kept on the sleeve, and they don't hurt the consumer. Because you know that when glass bottles break, consumer can be hurt because of cuts and flying fragments and so on. So typically these shrink sleeves protect against break and can be used, an approach used to further decrease the weight of the bottle for environmental reasons, economical reasons, whatever. If we have a bottle that we have more sure about that is protected, we can use less glass, less weight, and decrease the overall impact of the bottle. Okay? So the last point of the production is inspection and quality control. Inspection is for some points are inspected to 100% of the production. So all bottles are inspected, like problems on the finish, because finish is the part of the bottle that will stand high pressure because of the application of the cork or crown cork, or any closure system will make force on the finish, and there are several characteristics that are inspected to the full production. There is also online visual made by human. So companies, industries, they have persons looking into the bottles, and these persons, they have very short shifts. They stay there for 20 minutes and then they change, because it's very much tiring to search for defects by eye. So but there are still the need, because there are no machines to look for some problems. And then there is sampling and testing in the lab for a few characteristics. The defects can be classified into critical defects. So are those that are very hazardous for the consumer, or that can make the container completely unusable, like birds' wings, spikes, thin little pieces of glass left inside. So they are very critical defects. Then we have major defects, are those that reduce the ability of the bottle, may affect its performance. So then it depends on the defects. And minor defects are those that are just visual problems, and they may affect the appearance by the acceptability by the consumer, but they don't pose a risk to safety, okay, or to the equipment. For example, a bottle that damages the equipment is also not acceptable. Okay. And then, before we go to lunch, we can see the considerations on bottles design. And that's maybe important for us that not work in the industry of bottles, but on the food industry. So we want to select a bottle to our product. And have you ever seen champagne in square bottles? Why? Why do you think so? Why nobody thought about, I will differentiate my product, I will put champagne in a bottle looking like a whiskey, so it will differentiate for sure. Yeah? We see whiskeys or these type of beverages in this type of bottles, right? Let's call it square bottles or rectangular bottles, but we don't see champagne. Why? There is a reason. Round bottles have higher ratios of resistance per weight and volume per weight. So, saying in a more easy way, circular bottles are much more mechanical resistant, rather than square bottles. So if I have a champagne has a very high pressure inside. How much is the pressure of a champagne? Coca-Cola. 4 bar for Coca-Cola. Champagne, 6 bar. So it's a huge pressure inside. We need a heavy bottle, glass bottle, to protect from breakage. So if we use a square bottle that per se has lower resistance as compared to the round bottle, we would need a very heavy bottle. So we use square bottles for those products that do not have internal pressure, that do not are heated like thermal treatment, typically we have lower velocities in the filling line. So for products with lower consumption rate, where the products are filled at lower velocities. The finish, as I indicated before, is standardized according to the closure. And we have here the link for the International Technical Center for Bottling and Related Packaging, which is the European center where you can find all standards for the closures, the dimensions that are standards for the different types of closures. Okay, so you can consult here and find here further information. Any question? No? About the neck, okay? About the neck, we have served, all of us, we have served some liquid from a bottle, and we know that the bottle, the liquid, to go out smoothly, the air must go inside so that the liquid does not go. Okay, so we want a smooth movement of the liquid. We need the pressure to be replaced inside the bottle, so the air needs to go in as the liquid goes out. And this is regulated by the neck length. Very short neck does not work so well. Longer neck works better. So neck regulates the air displacement. The shape and size of the neck are important for bottle filling and service. So it's not only when the bottle is being empty, but also before when it's being filled. And also, the neck is important to accommodate variations on the volume of the product due to temperature fluctuations during the storage. So I think everyone, some time to time, have put a bottle on the fridge to cool down quick, and if we forget the bottle there, we know that the product comes out because there was not enough neck to accommodate the increase in volume when the product freezes. So neck is also important. This is an extreme example, of course, but in the regular use, when we have a beverage with gas, so with CO2, and temperature during transportation, during summer, there are changes in temperature, and this leads to changes in the internal pressure, and the bottleneck is important to regulate and to mediate that. Then we have the shoulder and the heel. So the shoulder and the heel are vulnerable areas of contact during the filling lines. Is in the shoulder and in the heel that several bottles touch each other in the filling lines. And we see different shapes of shoulders. You see, this bottle has a slope of the shoulder more higher than this. This is more smooth shape on the shoulder, and this also imply that we will have different stacking resistance. We will see that a little later. So the body supports the label, okay, and it's important that the design prevents abrasion between the two labels. That's why we have in some bottles a little bit inside, so that the label is going to be placed in a position that will not scuff with the bottles that are on the same, that are next to that bottle. So the label is not scuffed, the printing is kept, and the appearance is better when comes to the consumer. Finally, we have the base and the gravity center of the bottle. So the design of the bottle influences where the gravity center of the bottle, and the gravity center is very important to what? To the ability of the bottle to stand up. If we have a very tall, very thin and very tall bottle, the stability on the filling line is not so good if I have a shorter bottle and wider bottle, right? It's not so elegant, of course, but this is a balance. So if the base is wider, if the gravity center is lower next to the bottle base, I know that my bottle is going to be more stable. I know that I can run my bottle in faster speed filling lines. If I want a special bottle, very tall, very elegant, okay, I need to decrease the filling line speed. I need to fill slowly, so I don't have such a good productivity. So it depends on the use, it depends on the product, so the shape, the overall shape will also be different. Okay, regarding the physical and mechanical properties, like for the other systems that we saw previously, dimensions are important, of course, also weight and capacity. Then on the mechanical properties, we have the resistance to internal pressure for products that are like carbonated, and in products that are thermal process impact. So during this process, the internal pressure increases. Then we have the vertical load that's important during the corking or capping, filling and closure application steps, and also during the storage where the stacks of bottles are made, and resistance to impact, especially during the filling, so the impacts in the filling line and a little bit also later in the transport are very relevant. Under the thermal properties, we know that glass is very resistant to high temperatures, very resistant to low temperatures, but glass is poorly resistant to the rapid change of temperature. So the shock, the thermal shock, is what kills the cat. So thermal shock resistance depends on the thickness of the material, in a way that the thinner, the more resistant. While mechanical properties is the opposite. The thicker the glass, the more resistant the bottle is. So we need to balance these two characteristics, because we want, in some cases, we want both. So we need to optimize, and we want to decrease the glass weight somehow, but we need to take care of the mechanical resistance. And then we have the optical properties, where color and light transmission are important. Color because of the appearance, consumer attraction, but also in terms of light transmission regarding the protection of the product. As you know, there are products that need to be protected from UV light, for example, and this means that colored glass may result better in a longer shelf life. And finally, we have the closure system that must guarantee integrity and also the opening torque. So we want people to be able to open the bottles with reasonable force, to be like that. So this means that the opening torque is something that we need to take care as well. So the thickness and the thickness and the weight are important measures. As I said, because they influence a lot of the physical properties, and they are selected according to the product and to the function and according to the mechanical resistance required. And there is a trend on decreasing the weight of the bottle. And there is a lot of developments, like the press and blow process that we have seen before, and other tools in order to make bottles lighter but still resistant. So this is where great developments have been occurred. The capacity. Okay, we know what is that's the internal volume. There are two measures of the capacity. We can really measure the capacity up to the top, and there are some bottles which is not the case, where there are some marks here that say something like 26 or 33 centiliters at 26 or 66 millimeters. So, sorry, I need to write here. So there are bottles that say for example, this is quite common in beer bottles of 33 centiliters. Okay, everyone can see this? So this means that if the bottle is filled up to, let's say, 6 centimeters measured from the top, it is guaranteed that the content is 33 centiliters. Okay? So this is a relationship between measuring filling height and content and capacity. So, but this is true only for some bottles. It's not always. So in this case, we don't have that. So I cannot show you, but maybe later in the wine bottles that we have outside, or beer bottles. We can check that later. So that's what I mean for it's the internal volume of filling up to a set filling level. These bottles are used in machines that fill by level. So they fill by level independently of the content, and because we need to have legally the minimum content, so these bottles are made in a special way with this relationship between the filling level and the capacity. Anyway, when we measure the capacity, we are able to verify or to control if the forming process and if the molds are still in good conditions, and we can also control the filling process, of course, and of course the net amount of the product that is legally, as Professor Lawosky showed yesterday, for those that have that E on the label. It means that the content has been controlled according to the specific legislation. Okay. And these are some data taken from literature, and interestingly, there is a trend for bottles of red wine to be heavier than bottles of white wine, and there is no technical reason from the wine or the bottle point of view to be like that. Is that the marketing tradition? And also there are these trends that the weight of the bottle is higher when the price of the wine is higher too. And also today there is no technical reason for this to happen, but for the marketing, these are data from 2012, so it's interesting to check if the market is still with these figures, or if is changing and using lighter bottles are more the trends due to environmental pressure. Okay. Regarding the mechanical properties, the strength of the container is determined by a combination of these 4 factors. Number one, or not exactly by this order, but surface condition is very important. If we have a bottle with scratches on the surface, these are going to be much less resistant. The glass weight, as I indicated, the more weight, the better in terms of mechanical properties. Shape, we will see a few examples that are shapes that are like the one on the circular or flat that I explained this morning, and also of course depend on the applied stresses, the speed of the lines, and the particular conditions. This is a picture of a micro scratch. So if I have my surface completely pristine, completely unscratched, I would have much better resistance. And this is why we apply those surface treatments that we mentioned in the morning, is to allow for better resistance. So this is we can I think that everyone saw sometime the CSI series, okay, when they are starting to look into the fragments and they immediately issue a report on the a lot of information. Okay, this is serious, but it has a true background. Okay, so by looking into the fragment of a bottle that was broken, we can learn and say why the bottle broke. And we know that the glass breaks more by tensile forces than to compression forces. So when we stretch apart glass somehow, we can break it. When we compress it, it's much more difficult to break it. So when we are looking for fragments and for a bottle that broke in the line, for example, we need to go and look into the spots of the bottle where tensile strength could have been applied. And this is why we also know that, for example, a bottle that breaks due to lack of resistance to internal pressure, it breaks with this type of patterns. So if we see the fragments, we can see and look for the origin where the defect was that with the increase of internal pressure made the bottle grow. And as I indicated, when we have micro scratches in the surface and then internal pressure inside the bottle, that makes to pull this apart. So the internal pressure acts as a tensile forces on the outside of the surface. So this is why the bottle breaks. And we have here examples of how the resistance decrease when during the life of the bottle. So at the beginning, after production, it can resist to 5,000 kilopascal, but then with the transport into the filler, it loses half of it because of touch and scratches, small scratches against the surface, and after long-term use, it loses even further. So this is very important when we want to reuse bottles. The bottles must be produced with higher weight because we need to have higher resistance, and we need to have better surface coatings in order to avoid scratches, not only because it's not nice to see the bottle all scratched, but also because the mechanical resistance decreases. So the risk of breaking during the second life or third life is higher. Okay? Do you understand? On vertical load, so as I explained, stacking or even, so stacking is a long time static load, but we have loads applied during the filling because the pieces of equipment on the filling line and the capping and so on. So, as I said, high-speed filling, closure operations, and so on. And a lot depends on the shoulder shape. So you see here a champagne type of shoulder can resist to 5,000 kilos, while let's say a squared type of bottle, it resists only to around 200. Is a kind of intuitive. We can see that because if we press here with the stacking forces, the shoulder will be submitted to tensile. Although we are compressing, the shoulder will be subjected to tensile strength. So that's why shoulder is so important for the vertical load resistance. Okay, so we have some constraints, some limitations on the design of the shape of the bottle, depending on the use that we want to give to the bottle. Okay, impact resistance. We may see a different pattern of fracture. In this case, we can see origin, and then we see a different. Remember the other one? The other one, we know that we have two Ds, one D and one inverted D. So when we are searching for the cause and picking up the fragments, we look for these two pieces of glass, completely different in this case that we don't have a piece of glass with a D shape. So this depends a lot on wall thickness, on the bottle diameter as well, and on the specific zones of impact, if it is on the heel or in the shoulder or in the body. For the thermal shock, so we have a thermal shock. So is the ability to withstand sudden changes in temperature, and so as I said before, steel glass resists well at high temperature, resists well at low temperature, but resists not good to a sudden change. And it's easy to see why, when the bottle broke due to thermal shock case, because the type of fracture is completely different. And where is the origin in this case? Is on the base, on the bottom, or on the base. And why? Remember that I told you that the thermal shock depends on the thickness of the bottle, and the thinner, the better. And the bottom is the thicker part of the bottle. So this is why it breaks there, because in the bottle it has the thickest part is on the base or on the heel. This is why the fracture origin starts there. Okay? Now, a little bit of homework. If I have these two situations, I have a hot product on a bottle, and I suddenly cool down the outside by placing, for example, in a stone bench that is cold. So giving rise to a certain difference of temperature between inside and outside, where the hottest part is inside, and compared to the opposite situation, I have the same bottle with some iced products, and I suddenly place it in a disk of the stove, for example, which is hot. So I create the same difference in temperature between the inside and the outside, but the order is different. We have the hot outside and the cold inside. Okay, and you may think if this is the same. Okay, probably not, because otherwise I would not be putting this here. And I ask what is the more probable causing break, if it is this one or that one, and why. Okay? So not to think now, otherwise we will not progress. About the optical properties, anyway, the answer is on that slide, so you can go back there later. The optical properties, we have here some transmittance or transmission spectra with the different wavelengths and 4 different colors of glass. And just see that the flint, that's this one, it really transmits above 80% of the light in nearly all range of wavelengths. While, for example, this one here, this amber, it absorbs, so it does not transmit into the in the UV range of wavelengths, and it transmits more in the visible portion of the spectra. So this is why for products that need protection we use amber bottles or some greens, some color, because we have better protection. In wines, for example, in port wine, a typical product where I come from, for vintage wines where they are remain in the bottle for 30 years, 40 years, 50 years, we use black color. So it's not amber, it's black, it's complete opaque. So there is zero transmission in all wavelengths. And we have here some information on how we can color, which are the coloring agents that we use or that industry uses to give the different colors to the glass. Okay? So we have then others like the closure system integrity and the opening torque. And so opening torque is measured by machines like this, where we have a base and we have well, this is a picture that was made to be nice, but in fact we place a specific accessory here that we turn and we measure the torque required to open the bottle. And this is very important to be addressed according to the specific consumer trends, because we have, for example, males, typically they can have higher torque strength than females, is natural. There are also the possibility to measure the force required to open a bottle with a cork, so the pull of a cork, and this is quite important. Any question?
No, I'm just wondering that the torque of male is in the highest level when they are 50 to 60 or 40 to 60. I always know.
Yeah, is when males want. Yeah, no, this was you can check the details. This was just an example. There was probably a reason why, and for a specific type of cap or so. Yeah, because should be maybe on the 20s. But maybe on the 20s they don't consume so many beverages requiring a torque rather than something like that. Yeah. Finally, a little bit on closures, and later we will have a topic on corks specifically. But closures, just some notes on closures. We have closures to retain the internal pressure. So they are designed because and for those beverages that have internal pressure inside. And we have like the crown cork, like here. So we have a metal part and a gasket part that is today is made out of plastic. Some used to be PVC. Now PVC has been replaced, and there is another plastics. In fact, this is called steel crown cork because the first systems there was a cork disc acting as the gaskets. So this is why it is called crown cork. And we have also this roll-on tamper evident. It's called roll-on because the way it is applied, and is tamper evident because when we twist off out the cap, there is a little bit a ring that remains on the bottle to give the evidence, provide the evidence that the bottle has been opened before, and can be used to retain internal pressure or not. No, okay, so it's for carbonated or non-carbonated beverages. We have closures that contain. So here we have plastics and cork stoppers. We may also have screw cap for powder products like coffee mixtures and these that are just screw type of closures. And then we have this common also for vacuum products, and this is typically called a twist cap because it is applied by twisting and is removing by twisting out. So it is one type. Often this twist cap has a special feature here that allow us to verify if there is still vacuum inside, because once it is open the lid goes pop up. So it means that it has been opened before, it has lost vacuum. So it's also a evident feature, gives opening evidence feature. And today a lot of systems are designed in a way that to protect, for example, in food, beverages, but also in pharmaceutical products, in products, cleaning products, to avoid children to have access to bleaches and detergents and these things that are dangerous for childs. So the closuring system is a key aspect on protection, on security, and to avoid children or elderly, for example, in the pharmaceutical area. Some elderly must be limited to access to some medicines, otherwise they can take over the dose. So closures is another topic that we could have a full lecture on this. Okay. So I think this was the end of the glass packaging. Do you have any question, any comment?